Hello, in this video we're in the multiple linear regression setting and we're looking at ridge regression, and we're in part 4. And so it would be wise to go back and watch parts 1, 2, and 3 before you watch this. But here we're going to look at we're going to put our regression model in canonical form and then perform ridge regression and see what happens. And ultimately nothing happens, and I'll show you. So here's our model, and we have to assume that it's centered and scaled, and then we write it in canonical form. So basically we multiply the identity matrix in there. And so this is a well-chosen identity matrix. These are orthonormal eigenvectors for X transpose X. Now we write V prime B as gamma, and then this is the design matrix. So essentially what we're doing is we're rotating the axis in a very special way. So the least squares estimate for gamma, then remember this is kind of the new X. So it's X transpose X inverse X transpose Y. So that's the least squares estimate. Now the ridge estimator for gamma in this setting is we add a small number to the diagonal elements of this down the ridge. That's actually why they call it ridge regression. And you do that in this way. So it's an identity matrix times K, which is called the shrinkage parameter. And the reason we do that is that with multicollinearity, this is on the inversion unstable, but we're adding down the ridge, adding a small number down the diagonal elements makes it more stable and actually reduces the variance in our estimators. Okay, so that's the ridge estimator, and we want to show that we can recover the original ridge estimator from the ridge estimator in canonical form. You just pre-multiply by V. So we have V gamma hat, and we write out what our least squares estimate of the ridge estimator is. And here, and so notice that V prime V is the identity matrix, so it's actually the same. So we left factor out a V prime in this, and we right factor out a V, and then we distribute the inverse, and we get this. That's the identity, this is the identity, and then we're left with this. But that is the original ridge estimator that we showed on part 1 and actually part 3 when we derived it from scratch. And also you can go backwards. If you have the ridge estimator, the original ridge estimator, you can take it times V prime to derive back the original estimator, right? And you can almost see it from here. Left multiplied by V transpose, and that's the identity, and then you get this. Now let's show that the mean square errors are the same, whether in canonical form or the original, data or the original model. So here the mean square error is this. Now we showed that here that this is the case, so we plug in V prime R and V prime R, but the gamma was V prime beta, right, in both of those. So now we left factor out a V prime, and then we hit the transpose. Here we left factor out a V, and then we have this. But this is the identity matrix, and we're here. So the mean square errors are the same. So we're really not gaining or losing if we use the canonical form versus the original. Now, one of the big goals of ridge regression is how to choose that dang shrinkage parameter. There are so many ways to do it, and a lot of it is through graphs, and it becomes an art because there's no limiting value. So as K goes to infinity, there's really no limiting value. So you want to pick a value where the estimators become stable, low variance, lower variance, that you try to keep the bias as small as possible. And so that's the goal of this. And so I'm just going to read off a few things and not go into them and say you really need to investigate each of these to understand what they're doing. But the ultimate goal is to just try to find that best K, where it keeps the variance, as you know, it reduces the variance, it keeps the bias small. But I do want to cover one thing. So the ridge trace, the variance inflation factors are low enough, maybe less than 10, that's an option. Press statistics and CP Mallow deal with, maybe you want to use a ridge regression, you know, in estimating or predicting. You have cross validation, and this DF trace is also another popular one. But and DF stands for degrees of freedom, and it's actually the trace of the hat matrix in ridge regression. And we're going to drive that and call it quits for ridge regression in this little series. So the trace of the hat matrix in ridge regression is this. So normally it's X transpose X inverse X transpose, but we have the shrinkage parameters in this matrix here to stabilize this inverse. Now, since it's the trace, this matrix can be moved to the front and we're left with this. Now we decompose this into the spectral decomposition of X transpose X in the same way here. And so this is a set of orthonormal eigenvectors associated with this. And these are the diagonal matrix of the eigenvalues associated with these orthonormal eigenvectors of this. I is the identity, so it's V transpose, and inverse. So everything is the same. But now when we factor out a V from here and factor out a V transpose and distribute the inverse, we get this. Right? And then you distribute the inverse, and then you get a cancellation. V prime V goes away, and we're left with this matrix here. But now, since we're still in the trace, we can move that matrix to the back, and V transpose V is the identity matrix. So now we're taking the trace of a diagonal matrix, which is actually very easy, very straightforward. And so the inverse of a diagonal matrix is 1 over these elements, and we're taking it times D. So this ends up being the sum of the lambdas divided by lambda I plus K. And so a lot of times in this DF trace, you see this quantity and you're like, where the heck did that come from? Well, it's the trace of the hat matrix. And so that's the degrees of freedom associated with it. Well, I hope you enjoyed this little mini series. There's 4 parts. I really did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.